Hey everybody, today we're working with levers, and for part A we are going to position our weight at 10 centimeters, and maybe what I should do is back up with how we set this up. So I have a piece of duct tape holding on the tape, I have my dowel, I slipped on a little black binder clip and I clipped it right at 0, and I want to make sure everything is tight on there. And then I have a little rubber stopper like a pencil end on there as well. When I take my spring scale and I measure, I'm going to see that this weight weighs a little more than 2 newtons. And what I also needed to do is zero this in, and so this will slide up and down for zeroing purposes. So right now I want to make sure that that little line is right at the 0, which it is. And then when I hook on my weights, I will see it should be a little bit more than 2 newtons. So it's like 2.4 newtons of force. So I'm reading on the side there, 2.4 newtons of force is being pulled down with our weight. So now I'm going to plot my weight, and it doesn't matter which side you use. I'm going to hang my weight at the 10 centimeter mark, and that's going to go with experiment A here. And notice that that weight pulls that down. But on experiment A over here, it says lever experiment with the load positioned at 10 centimeters. So the load is going to stay at 10, but we're going to position our spring scale, our effort, this many centimeters from the fulcrum. And so 2.55, 10, 15, 20, 25, and you'll notice that those are the marks already on your ruler or meter stick here that's been cut. So we have our spring scale connected, and we're going to go all the way in to 2.5. And when I go all the way into 2.5 and pull down, I pull down, whoa, I'm not even level yet, and level. So you have to pull it level, and then your partner will have to help you, and I can see, whoa, that's pulling down very, very far. So it is a little more than 9 newtons of force. So I'm going to call that 9.5 newtons of force to pull down. So on my paper, when I have my weight at 10, it took me 9.5 newtons of force. Now, noticing this may have been a little bit over, so I'd want to double check to make sure it's right at 10. That's what your partners are for, but you'd write 9.5 here. Now, because you're pulling down and the weight of the spring scale and the force, you're going to add 0.5 newtons. All right, so you're going to add 0.5, so that would be a 10 for me. So 9.5 and 10. All right, we will help you with graphing that, but first we want to get all of our data into this little table here. All right, so now I'm going to make sure my weight is back at 10. I noticed it slid. I don't remember if it did or not last time. That's what your teamwork and partners are for. Now we're going to go to 5 centimeters from the fulcrum, and now as I pull down, you'll notice that I get a new number, a different number, and it's going to be less. And so I'll record that number. Once I get it level, record that number, and then add 0.5 to my second column. Add 0.5 to my second column, and you do that for all of those centimeter marks there, making sure your weight, your load is at 10 centimeters. We will then graph it and make some predictions. What I really want you to notice is I want you to notice the relationship with the distance from the fulcrum. Okay, when I move this spring scale, when I move my effort away from the fulcrum, what happens? And so that's really what I want you to pay attention to. What happens as you get further from the fulcrum? What happens as you get closer to the fulcrum with your effort? Just a quick little reminder, this is my load, this is my weight, this here is my fulcrum, it's my balancing point, and this spring scale is measuring my effort. So as I move my spring scale, I am moving my effort around this lever. And so hopefully you'll start to see the mechanical advantage of the lever. This is part A. Okay, this is part A of our experiment. And so go through part A. Part B now is different. So this is where you may want to pause this video to do part A and then come back to part B. Or you can do both and then experiment with both. But part B, your paper says now you're gonna have the effort at 10 centimeters. All right, the effort will stay at 10 and you're gonna move your load. So this is the opposite. So this time you are always gonna keep your spring scale at the 10 and you are going to move your load. Okay, so you're gonna start with your load at 2.5 and you're gonna measure it level. All right, and then you're gonna move your load out to 5 and then out to 10, out to 15, but the difference is negligible once you start to move it. So go ahead and check those. It's a little tricky in the insides, but I think you could do it. Measure it, all right, and then keep moving out for each increment. Share with each partner there, and then as you go, again, measure it with the spring scale. Write your answer in this first box here, and then add 0.5 newtons to account for the weight and pull of your spring scale on here. Go ahead and get all your data on this, this table and chart. Then we'll help you create the line graph for this. And then again, I want to take a look and see what is the relationship with the distance that your load is moved from your fulcrum. What's the relationship? Is it easier? Is it harder? Depending on the location of the load, or is there no difference at all? So part B, you move the load, all right? The effort stays in the same spot at 10, so the spring scale stays at 10 for part B. And part A, it was the exact opposite. Part A, you are moving the spring scale and your load stays in the same spot. So go ahead and do part A and part B, noticing where it is easier and where it is harder, more difficult, heavier, greater force is needed. So we measure force in newtons. So we're measuring our force using our spring scale and our lever setup here. So this is levers, part A and part B.